partition, partition, partition. That is not what you hear every day now, is it? What it simply is, or what it means to partition something, is to split it up. And in this case, we'll be using the system AX equals B, and we're going to split the matrices A and X in the most convenient fashion possible. So here we have our systems of equations that gets turned into an augmented matrix. Now, fundamentally, if we have A is equal to a matrix of A sub 1, 1, A sub 1, 2, all the way down to A sub 1 times how many columns matrix A will extend to. And we can do the same for the other rows, where the second row is A sub 2n, and as we go further down, we can insert as many rows as we want, and the overall pattern here is that A can be as big as M and N can be. Let me just touch this up a bit. And I'm going to shrink down the font. Now, as for X, we know X is usually a column vector, and it goes from X1, X2, X3, all the way down to how many rows this column vector has. And the same principle applies to B. We have B sub 1, B sub 2, and as many rows as B can have. So, if the coefficient matrix, the column matrix of the unknowns, and the right-hand side, respectively, of the M cross N linear system AX equals B, then what we can do is we can refer to this setup right here, and we can actually consolidate the two terms such that A and X will both simply produce a result of B. And in doing so, we can multiply these two matrices, and we get a result of A sub 1, 1 times X1 plus A sub 1, 2 times X2 plus A sub 1, 3 times X3 plus as many columns as there is in first row times how many X terms there are in the system. And we can do the same for the second row with A sub 2, 1 times X1 plus A sub 2, 2 times X2 plus A sub 2, 3, A sub 2, 3 times X3 all the way down to A sub 2n times how many n terms there are, and we can go infinitely long, or how much longer we choose to, such that we get A sub m1 times x of 1 plus A sub m2 times x of 2 plus however big the coefficient matrix is, and however terms there are of x exist in the system. And after multiplying the two matrices together, it will still produce the result of B. Now, one thing that I hope you guys notice is that there is a term that can be factored out. I'll have you guys guess what it is. And if you guys said that it is your x terms, you would be correct. To demonstrate, we can do x sub of 1 times a sub 1, 1, a sub 2, 1, all the way down to how many columns the coefficient matrix has. And we can repeat the same process. We have a sub 1, 2, a sub 2, 2, and how many rows, however many rows x of 2 has. And the same goes for n terms. We have a sub 1n, a sub 2n, and a sub nn, which once again still equals b. In other words, a of x is equal to a sub 1 times a sub 1 plus x of 2 a sub 2 plus how many x terms and n terms there are, all which still equals b, where a sub 1, a sub 2, and a sub n are columns of matrix A. And as a result, our columns are what's called as linear combinations. And our x terms will end up being simply coefficients of the system. And that's pretty much it for partition matrices. So let's recap a bit. Partition matrices are a way to split up a matrix and present it in the most convenient way possible. Over here we have the infamous equation AX equals B, and let's assume that A, X, and B can be as big as they can be. And our n terms, our n, m terms apply to all real integers within the system. So that's clear. And we know that Ax equals B. We know that the coefficient matrix A and the x column vector can be multiplied together. And as a result, we get this expression right here. After doing that step, we were able to factor out our x terms, and we're still keeping the notion that the matrix can be as big as it can be, and we present that by presenting m and n terms. So in this step, the x terms are factored out, and we're able to notice a pattern here where it's x sub 1 times a sub 1 plus x sub 2 times a sub 2 plus however many x terms there are and however big our coefficient matrix is. Once again, it all equals b. So let's say we have a linear system as shown. Given what we've learned about partition matrices, Gaussian elimination, and well, that's pretty much it. how can we use those two principles to find the solutions for this linear system? In other words, what are the values of x1, x2, and x3? There are two ways. Well, there's actually one way. So first off, we know the protocol. This has to be converted into an augmented matrix. We have column 1 consisting of 1, 4, 7, column 2 consisting of 2, 5, 8, and column 3 consisting of 3, 6, 9. With the last column being 0, 3, 6. To find the solutions, we will apply Gaussian elimination, and in doing so, you guys can do the math yourself. This is where I'm going to have you guys pause and figure it out, or you can plug into your graphing calculator. Either way, what you should end up with is x1 is equal to 1, x2 is equal to 1, and x3 is equal to -1. Hopefully you guys arrived to those solutions. Now, given our solutions, I want to present it in a way that requires a partitioned matrix. So referring to this example right here, we're given the x terms and we're given the coefficient matrix. Therefore, it's all a matter of plugging everything back in. As a result, we get 1 times the column vector of 1, 4, 7 plus 1 times the column vector of 2, 5, 8 plus -1 times the column vector of 3, 6, 9, which is equal to 0, 3, 6. That is, B, noted as 0, 3, 6, can be expressed as a linear combination of the columns of A. This representation of one column vector in terms of others is a fundamental theme of linear algebra. So just like how you partition A into columns and X into rows, it's often beneficial to consider an M cross N matrix partitioned into smaller matrices. So what I mean by that is you can partition the matrix like this: 1, 2, 0, 0, 3, 4, 0, 0, and this is the matrix after you apply Gaussian elimination. And we can partition the matrix that isolates our 0 values, and while doing that, we end up finding our solutions. However, we can break the matrix into several column matrices where we just have C1, C2, C3, and C4. And to present that visually, this is what we have right here. The same can also be done for row matrices, where we can split the matrix into 3 rows, and as a result, we get a column vector of R1, R2, and R3. And there you have it. So we're now able to incorporate the partition matrices, and in doing so, we're able to present our solutions as simple as it can be. Well, good luck everyone, and I hope this video was helpful. Do not forget to like and subscribe.